Hello? Yeah. Right. Uh, so this is for grade 11 physics, right? So as soon as you join, if I hear that you are not muted, I have to unfortunately mute you so that you don't make, it doesn't cause a disruption. All right. So what we'll do today is quantitative aspects of chemical change. But before we start, I'll just make sure that we wait, let's say, for 5 minutes to see if we can get more people to join so that when we start, at least we have most people who have joined, right? Please mute yourself, guys, so that you don't disrupt the lesson with your background noise and so on. If you have any questions before we start, just ask. But we will start in at 35 because we're waiting for a few people to join, right? Meanwhile, if you have any questions whatsoever, you can ask.
Sir,
Yes.
uh, in this lesson, are we going to be able to see the periodic table so that we can like know our elements?
Yes, I'll show you the periodic table.
I
But you guys should have periodic tables as well there.
yeah, I can find mine.
Okay. All right, guys. So I think we can start now. Anyone that is yet to join will probably join at some point during the lesson, right? So my name is Pilani Dlamini, and I'll be taking you through quantitative aspect of chemical change. Well, this is part two. We did a part one, I think, on Monday, if I remember correctly. So on part one, obviously, we covered the moles, we did Avogadro's law, and so on. So in today's lesson, we have all these things that I've listed here, which we will cover, right? Let me just do this. So the plan today is to make sure that by the time we are done, we have at least done everything in this list, right? And not just done all of that, but you should be able to at least comprehend or understand how to explain or calculate any of these things. Okay. Now, let's start with the first point, this one. So, I want to be able to interpret balanced equations in terms of volume relationships for cases, right? I mean, for gases, sorry. I don't know why I said cases here. It's gases. Now, what happens is, if you remember Avogadro's law, okay, let me change this color to black. All right, black. Is it? All right, so we'll start with the first point. If you remember Avogadro's law, it says, well, at a constant temperature and pressure, the volume of gas is directly proportional to the number of mole of gas. So in relation to our first point here, right, we want to be able to interpret any balanced equation in terms of volume relationships for gases. What does that mean? When you have an equation like this, say you have, this is point one. Let's say you have an equation where hydrogen reacts with oxygen to give you water, just a simple one. So you have H2 reacting with oxygen. Okay, let's do this. H2 reacting with oxygen to give you say water vapor. Right, so water vapor. I'll not do this. In this example right here, the equation I just wrote, if you remember, you must always make sure that your equation is balanced, right? But when you take this particular equation, at this point, it's not balanced. And then point number two, you see these G's, G, G, G. What do they mean? It's basically gases, right? It means everything in this equation is a gas. So even this water, it's not just water as a liquid, it's water vapor because of this G. If it was maybe H2O, say Q, right? No, not Q, AQ. This would be water, but in its liquid or aqueous form. Now, but for this example, we are focusing on gases. So a typical balanced equation of this form would have to have, okay, we need a 2 here. We are not balancing equations for today's lesson, so I'll just balance it out for you now. But you should have done balancing equations at some point. So in this equation, what the Avogadro's law, or actually what happens in gases is, if you look at this number, the coefficients, let me change. Let's use yellow. These coefficients. What these coefficients tell us is so for every 2 moles of hydrogen gas that we have reacting with oxygen, you produce about 2 moles of H2O gas or water vapor. So it means for every 2 moles So here's a good way of thinking about it. For every 2 patties that react with bonds, you get a burger, right? So in this case, for every 2 moles of hydrogen that reacts with 1 mole of oxygen gas gives us about 2 moles that's water vapor. Right. But remember, these numbers, these 2, and let me see, 1 mole and 2, these are not the actual number of moles of each of these constituents of the reaction. They are merely mole ratios. What do I mean by that? Let me do. So most people get confused with this one. It's very important to understand that before we move forward, these are what you call mole. Is this that I've already written. For every 2 moles of hydrogen gas that react with 1 mole of oxygen gas, you get 2 moles of water vapor. That's what it means, at least in this example. So the difference between mole ratios and the actual number of moles, remember, we use N is equals to. This will allow us to find actual mole. And this, however, let me see. We need to start and establish this so that when we move forward, everyone is on the same page. Insta, say we use, I don't know, that. What happens? Okay, let's say we use this one. Now let's move this guy here. Actual moles are not the same as mole ratios. These two are not the same. One tells us the ratio of what we need to react in order to get the final product, while the other one tells us the actual number of moles of either the reactants or the products. So a good example would be if they gave us a mass of hydrogen, we would definitely use our periodic table to find the molar mass of hydrogen and then find the actual number of moles of hydrogen. We will do this at a later stage, but for now, just know this is what happens. Right. So going back to our point, what we are trying to do here is to show you the relationship of these ratios for gases. What usually happens is if we have gases like this and they are given volumes, let's say we have okay, so this means we have 2 mole of H2 is to 1 mole of O2 gas, right? Is to 2 mole H2O. Okay, let's do this. Yeah, so if we have 2 mole H2O, For gases, the ratio of these is the same for the moles and also for volume. So what that means is we would have 2 is to 1 is to 2. This is our first point in this lesson. Only for gases. For other substances like your liquids or solids and so on, you can't get this relationship. You can only get it for gases. So, what this means is, remember, at STP, STP being standard temperature and pressure, we've covered this in our previous lesson, if you remember correctly. At STP, 1 mole of any gas occupies about 22.4 cubic decimeters of volume. Right. Now, let's say you have a question that says, let's do this for my question. If you have, can you guys still see my screen? Like, hello, let me see. Are you guys still able to see my screen?
Nah, I just show a P.
It shows what?
The letter P, I think, is of your account here.
Okay, I have to reach a.
I think you have to rerun the save.
Someone is sharing their screen. Who's this? Elton. Elton. Why is Elton sharing? Elton, why are you hijacking my lesson? Let's see. I think you pressed on the wrong settings there. Elton, please just stop sharing your screen because it's interfering with me sharing my screen. Or just log out and log back in. I'm not sure if Elton can hear me, but I'll just I'll remove. Yeah, fine, good. Let me share my screen again. Let's see. Aha. You guys able to see it now? Just a thumbs up there. You should be able to see my screen. Okay. Yeah. All right, good. All right. So now, if you have 44.8 cubic decimeters of hydrogen gas at STP, standard temperature and pressure. If you don't remember what this is, you can go back to our previous lesson. We already did it. So now, what volume of oxygen is required? So what this thing is saying is, for gases, right, especially at STP, or rather at STP, as long as we know these ratios, these mole ratios, we can also use them to find their respective volumes. Like in this case, our question is saying we have 44.8 cubic decimeters of hydrogen and it will react with oxygen, right? How many and what's the volume of oxygen that is required, right? Okay, I forgot to add my oxygen here. Sorry, guys. What volume? O2. Don't think you'll be able to see that. Let's do this and say quick example. You can't do this with solids, liquids, and so on, but only with gas. The volumes of water and whatnot, it won't work. So what you would do here now is, remember, the same ratios that we have for the mole ratios, we can actually use them for volume. So in this equation, we know that the ratio of H2, H2G to O2, which is our oxygen, is 2. Don't know why my pen is misbehaving. It's 2:1, right? These ones, they're the same. This guy. Now, we know the volume of hydrogen, right? We want to find how much oxygen we need to react with this hydrogen. What we just described says we can merely use these ratios. Now, let me show you how to do that. You say, you put your known here, which is 44. Sorry about that. My pen is misbehaving. Is to X. We don't know how much oxygen we need, right? So the simplest thing to do here, you cross multiply. If you're doing maths, of course you are doing maths because you're doing physics. You know cross multiplying is 2x, and then you multiply 44.8. You will use this, by the way, for the rest of your high school life, finding ratios in stoichiometry and so on, but you'll see it as we proceed. If you don't get it for now, don't worry. As we go on, you'll see it. Right. So now, if the molar ratio or the mole ratio of hydrogen to oxygen is 2:1, what about the volume? We know that it's 44.8 is 2x. Now, what is that x? We say x, and when we solve for x, it should be half of 44.8 is, for the sake of this example. So we know that if we have a volume of hydrogen, let me see, do this. Right. If we have this volume of hydrogen, and we need to know how much oxygen volume we need in order for these to react with 44.8 cubic decimeters of this hydrogen, now we know we would actually need 24.4 cubic decimeters of oxygen. This works for any volume, but for the sake of simplicity, I used the volume that you guys are used to, which is the standard temperature and pressure volume, 24.4. Right, let's move on. Now, let's say quick example number 2. On the same page, quick example 2. Right. Let's say you have a reaction, combustion reaction. You guys probably haven't done those yet, but for the sake of this example, it should be fine. Let's say you have CH4. CH4, for every combustion reaction, you need to have oxygen, right? And you'll always produce carbon dioxide and water. Right. CH4 is a gas, by the way. It's a methane gas. When you fart there, just know you are releasing methane gas, guys. I'm kidding. I don't know what you're releasing. But now, and carbon dioxide, I want to make sure that you know that these are gases, because this rule is only applicable to gases. Never try to use it anyway. I will keep saying this until you are tired or you will dream about it in your sleep. Only for gases, right? Nowhere else. Try use it somewhere else. Just know you are breaking the laws of physics. We have these gases here. And then this equation is already balanced. You don't have to balance anything. Now, the question says, Find the volume, let's say, of carbon dioxide produced when, let me see, let me write it for you. I'll use just a simple volume. Find the volume of carbon dioxide gas produced produced before I continue, so far, are you guys able to see my handwriting? Sometimes I can write a bit too squiggly and whatnot. Just raise a thumbs up there. Good. Thank you. Find the volume of CO2 gas produced. Yeah, thank you. I see the thumbs up. Thank you. You guys are interactive. That's very good. So find the volume of carbon dioxide produced when 11.4 cubic decimeters, right? Okay, let me use 11.2. We've been using too many fours now. Of CH4 is methane, is burned. Aha. So remember what we said. These ratios, where's my rate? I like rate. Here you'd probably have a 1, and then you have this guy. You'd have a 1 here, and you have a 1 here. If I know that the mole ratio of CH4 to carbon dioxide is 1:1, right? Let me write it. Let's say this is our solution. And we have ratio CH4 gas to CO2 gas. And our ratio happens to be 1 because of this coefficient, right? 1 is to, also next to carbon dioxide, there's a 1 there. And then now we are given the volume of 11.2 cubic decimeters is 2, and we don't know the the carbon dioxide, right? But at this point, if you can check, the ratio is just 1:1, which means the answer is simply 11.2, because if you cross multiply and divide like we did here, it'll just be ones everywhere. So seems like for CO2, let me actually underline these. Let me see. Okay, we have this one, we have that one, right? This must be, that's our volume, right? And we wrote it here. X is our unknown. Now, X, therefore, our X is 11.2 cubic decimeters. Right, we will do more sophisticated examples as our lesson proceeds, but for now, let's do this. This means the volume of carbon dioxide that is produced when we burn 11.2 cubic decimeters of methane is actually 11.2 as well. Therefore, 11.2 dm3 of CO2 is produced. This is a very perfect reaction. Usually in reactions, you can't burn everything and produce the same thing. Right. Now, this is what you would get. You can find any volume, actually. It can be any volume. It'll still be applicable. Right. Let me make sure here. I'll just say cross multiply. You guys can have a mental note there. Cross multiply. Yes, cross multiply there. Now, so that is basically what happens when you have gases reacting. The mole ratio and the volume ratio is the same. So since we will have 11.2 here as well, If you check the ratio of these volumes, it's still 1:1, because if you divide both sides by 11.2, you're still going to get 1:1. Same as here. The ratio, the mole ratio was 2:1. And then now we have X being 22.4, right? If you divide 22.4 here, 22.4 here, you'll still get 2:1. So basically, the mole ratio and the volume ratio of gases at STP is the same, always. That's our first lesson of today. Right. So remember, I said we will first cover this. At this point, we have, in essence, covered our first goal of today's lesson. So now let's go to our second one. This one, you even did it in grade 10. So I'm just going to run quickly past it, defining concentration and also calculating the concentration in moles using this formula, right? Even this one, we will move past it quite fast because we want to reach to the ones that are more interesting, these ones. Right. But I will still move fast and slow enough to make sure that you guys understand what we're doing. So let's go. Point number 2. Concentration. A good way of thinking about concentration is, if you remember, I'm not sure how many of you had tea this morning or tea at some point this week. If you remember, if you have tea and you take sugar and you pour it in the tea, some people prefer 2 spoons, some 4, some 8. I don't know why you would prefer 8. But anyways, if you do, the more you increase the number of teaspoons or tablespoons of sugar that you put in your tea, the sweeter the tea gets. However, the lesser number of tablespoons or teaspoons of sugar that you put on your tea, the less sweet that the tea will taste. That is, in essence, what we call concentration. It's basically the amount, if I can put it in physics terms, the amount, why is my pen doing this? The amount of sugar, not sugar, sorry, the amount of solute in a given solution. So obviously, depending on which textbook you use, this definition might vary, but still it describes in essence what we're saying here. And usually the SI unit of concentration is mole per cubic decimeters. Or some textbooks, they write it like this, moles. So don't be shocked if you find a nice textbook hanging around, but they write your concentration like this. It's still the same thing. So this is what concentration means. Moles per cubic decimeters. If you remember, moles is just the unit value that we use to count the amount of substance that we have. Right, but that's grade 10 stuff. Now, at this point, you should know what a mole is, right? So now, let us give you a simple example of how you would find concentration. Quick example 1. Quick example 1. So let's say you are given, I say, 0.8 moles of sodium chloride, and they dissolve it in, let me write it for you. 0.5, no, let's say 8 mole of sodium chloride. This is sodium chloride. It's basically your salt, table salt, dissolved in a volume of water, let's say 0.23 cubic decimeters of water. This is a typical example you would find in a test or exam. But in an exam, they'd add even more detail, of which we'll do that as we proceed with the lesson. We can do a few exam examples as well. Now, 0.8 mole of sodium chloride is dissolved in 0.23 cubic decimeters of H2O, water. Right. Now, the question would be find the concentration in this example. Remember, we said we will find our concentration, concentration C. Let me change color. Concentration C is N over V, where this N is in a given solution, right? C is equals to N over V. Now, what you might also find in other textbooks, they might say C is equals to M over MV. So what they did there is just they substituted the N from this formula. So they took this and substituted here. That's why you get this. But for now, for this example, let's not worry about that. But that's where that formula comes from. Now, C is equals to N over V, where N is our number of moles of the given substance. V is our volume of the solution or the solvent. Why am I saying moles? And then C is what we're looking for, the concentration. Okay, let's do this. To make things easy, we have this guy. That's what you'll sub in here, right? You have the volume. That's what we'll use to substitute here. And then lastly, we are looking for concentration, which is our C. Now, how would we do this? We would say C is equal to N over V, right? And then already we know that our number of moles is 0.8. And our C is, our V is 0.23. Now, what is our answer? Our answer should be, let me see. Find my calculator. Should be around 0.4, 0.38 to 0.4, 0.8 divided by 0.23. 3.4, yes, 3.48. Remember, in your case, you always keep 2 decimals. 3.48 watts, moles per cubic decimeter. Remember, guys, very, very, very important to have units all the time. Otherwise, what's this? Otherwise, one day, when you become a scientist or an engineer, whatever, you will kill people if you don't know how to use your units very wisely. So don't make that mistake. It's not necessary. So that's what we do. So this is how you would calculate the concentration, right? Now, here's a more interesting example where we'll use that formula, probably the one I showed you before. Say simple example number 2. Quick example number 2. I call them quick examples because you know the famous saying that says, in an example, you get 1 plus 1. In a homework, you get 1 times or 3 times 9. And then in an exam, you're supposed to calculate the size of the sun, right? Quick example 2. but you should be able to understand either way. Let's say you have 3.2 grams of hydrochloric acid and it's dissolved in 200 cubic centimeters of water. Let's do it. And then you are required to find the concentration of hydrochloric acid. This one will be a bit more interesting. You can't dissolve HCl with ice because it's already a liquid. Right, so you just pour 3.2 grams of hydrochloric acid in a 200 cubic centimeters solution. So remember, a solution, it means there's a solvent and then there's a solute. Solute is usually the liquid. Solvent, typically it's a powder like your sugar in tea. And then if we're talking about tea and sugar, the solute would be the sugar and then the solvent would be the water. Now, we're given this and find the concentration. Right. We know our mass. We know our volume. Right. And we also know our formula, which is, let's say, solution. Should I solve it? Okay, let's start this side. Solution. We want to use formula C is equals to N over V. Right. However, we don't have the number of moles. We don't have this guy. We are only given the mass. Number two, volume must always be in dm3, which is cubic decimeters. However, the one that we're given is in cubic centimeters. Right. So that is a cause for concern. That means before we can even substitute in this formula, we must first find the moles, and we must first convert as well the volume from cubic centimeters to cubic decimeters. Now, let's say one, convert from cubic centimeters. You will never in your life use cubic centimeters and moles in this particular equation. If you do that, it's completely wrong. You must first make sure it's in cubic decimeters, always. Right, so let's do that. Typically, when you convert from cubic centimeters to cubic decimeters, you simply multiply by 1,000. So that means 200 cubic centimeters divided by 1,000 will give us our actual decimeters that we're looking for. Divide by 1,000, right? Now we have our volume. However, we don't have the number of moles. And we know from our previous lesson that number of moles made. So in this case, we're given mass, which is 32 grams. We can find the molar mass using our periodic table, right? So if you come, let's see if I can get our periodic table here. Do I have a periodic table? Let's see. Where's my periodic table? Seems like... Aha. You guys should be able to see it. It's refusing to... You wanna do... Yes. Much better. Now, from our periodic table, we want to find molar mass of hydrochloric acid. But hydrochloric acid has hydrogen. What happened? Hydrochloric acid has hydrogen. Right. It has hydrogen and chlorine. Where's my chlorine? There. It was hidden by text. Okay. So if you check, hydrochloric acid has 1 as the molar mass, while chlorine has 35.5. Now we can use that to find our molar mass of HCl. Okay. So we have M. Let's use this. Molar mass of HCl is 1 plus 35.5, which is 36.5 grams. Remember, grams per mole. That's our molar mass. Now we can find the number of moles. N is M over M. Small m over big M, not big M over small m. Okay, that is 36.5. Our moles should be 33.2. 36.5 should be not point something. Yes, 0.08. Actually, we have to round off 0.09 mole. Now we have our moles, we have our volume. Now we can find the concentration. C is C is 0.09 over V is, we said, 0.2. 0.09 divided by 0.2 should be 0.45 mole per cubic decimeter. Obviously, there's a second way of doing this, which is that formula I showed you. So now we have everything we needed. We have our volume, of course, we did that. We had our, okay, this is our mass. And then we translated it to the number of moles, and now we're fine. So a simpler formula that would have taken a shorter time would be that one. C is equal to M over MV. So here you were going to substitute your 3.2, and you're going to take your 36.5 and your 0.2, and then you would have found 0.45 allegedly. Let's see if it actually is. Yes, 0.44. So in an exam, what they do, depending on which method you use, they put an allowance, say, they will say 0.43 to 0.48 are all the allowed values. Why? Because they know people will use different methods. As long as the method you use is correct, you should be fine. Right, so 0.44 is not that far off from 0.45. These formulas are both the same. The reason we got this one being a slightly smaller than that is because we were rounding off as we kept doing the steps. So this one doesn't round off this one. This one doesn't round off. That's why it gets us the most accurate answer, which is 0.44. So how did we get this formula? I showed you before. It's just taking this, actually this formula, this m over m, and substituting it in the formula C where you have n here. Then you sub it just here. That's how we get this being equal to Cm over mv. We basically substituted this n on this formula. But if you do it step by step, don't worry, you won't have to memorize any of this. All right, guys, so this is our second portion of today's lesson. So we've covered that. And now what usually happens is in reactions, sometimes, or actually not in reactions. Let me do this. We've done that. We've done that. Okay, we haven't done this. So usually what happens is for percentage composition, which is our next part, what usually happens is you would be given, let's say, water. And you just want to know how much oxygen is in the molecule water, or how much hydrogen is in water. Usually this is expressed, let me say, our next part or point for today is percentage. You must move fast because you still have just a nice example. Percentage composition. Right. So what happens is, given a substance, say maybe e.g. H2O, we want to know the percentage contribution or atom. In this case, we would want to know how much hydrogen or how much oxygen is in water. We usually express this in percentages. So how do we find this? Like how do we, excuse me, so how do we know the percentage composition of an element? So what we would do is we would say percentage of an element is usually equals to the molar mass of that element. This is too big. Molar mass for that element over, let me see, zoom in a bit. Yeah. Over the molar mass of the whole compound or substance. Times 100. Because remember, every time you're calculating a percentage, after taking the ratio, you multiply by 100 times 100. So let me give you an example. Quick example one. This one, we'll just do one example. It's not really a difficult concept or something tricky. However, you are more than welcome to bring more trickier examples or problems that you face in class and put them on the groups, and we will help you with that. Now, so in this example, you would have, let's use carbon dioxide. Seems like I lost connection. I lost connection for a bit. Please give me a thumbs up if you can still see my screen. Just to check. Thank you very much, guys. Okay. Now, quick example. Let's say you are given carbon dioxide. Or do you want water? Let's use water. Water is boring though. Let's use carbon dioxide. Say, let's say we find percentage of calcium, maybe, in calcium carbonate. Calcium carbonate is this type of salt. Okay, calcium carbonate, right. So the way you would do this is simply, you would first find the total, this guy, find the total mass, or molar mass, rather. This molar mass, you would need to know the total molar mass. Now what you would do is you'd say molar mass of calcium carbonate is equals to, we already know from our periodic table that calcium is about 40 grams per mole. I won't show you the periodic table again because it's a bit, it's a bit tricky to keep pulling it up. But you can always confirm these with your own periodic table after we're done with the lesson. Right. So calcium carbonate, it has carbon, calcium, and oxygen. Why do we have 48 here? Should be 3 times 16 actually. Right. Now, this would be 40 plus 12 plus 48. I assume you already know how to find the molar mass of any substance. It's the easiest concept as well. It's the basic thing you should be able to do. So I won't break it down on how it should be 100 grams per mole. Now, what is the molar mass? Okay, we have the molar mass of calcium. Now we need the molar mass of the element, right? We need, no, I can't use that. Now we need this guy, molar mass of the element. It's a very simple thing. We can say M, we were asked to find the molar, the percentage composition of calcium. So what is the molar mass of calcium? It is actually 40 grams per mole. Good. Now we can say percentage composition of calcium is the molar mass of calcium over the molar mass of the whole compound or substance times 100. This would give us 40 over 100 times 100. From that, you see what's happening here. This would be 40%. So in a sample of calcium carbonate, 40% of the whole substance contains of calcium. That means the remaining 60% belongs to both carbon and oxygen. Right. So you'd have to do the same thing to find the percentage of carbon or to find the percentage of oxygen. The very same thing. All right, guys. For this one, we can now move on. This one was quite a simple one. Is this guy? We found it. Let me just do that. Should be fine. Now, let's move to empirical and molecular formula. So from our lesson, we've already covered everything up until this point. I don't know what's happening. So now we want to find what's happening. Great. Now we would like to find the empirical formula and molecular formula of any compound. Right, let's do this. Move quickly. This is another interesting concept in chemistry. Empirical The easiest way to teach this concept is to just start outright with an example. There's no basic, you won't be asked on what is the history of empirical formulas, where do they come from, and so on and so forth. You just need to know what it means and what it does in chemistry for your own benefit. Though. But if you also can calculate it, it's even much better because you get all the marks that you want for this section. Okay, so let's do that fast. Molecular formula. So what's the difference? Right. So the way it works is if you are given a molecular formula would look like, let's say, I like underlining this so that you guys can keep up, even if I'm fast for you. At least you can see that, oh, the underlined parts, they correspond. Let's say this is empirical, and this is molecular and empirical. Now, a simple, quick example. If you have something like this, say you have C6H12O6. This would actually be an empirical formula. Molecular formula. Okay, don't know why it's not erasing. In a case like this, let's say they ask you to find the empirical formula for this. You would have to find the simplest ratio of these numbers, which are our subscripts. In this case, 6 is to 12 is to 6 is not the simplest ratio you can get for these specific numbers. The simplest you can get is 1 is to 2 is to 1. How did we get here? You always take the smallest number in a ratio and divide everything in that ratio using that number. So in this case, we use the 6 and we divide everything in the ratio with a 6. So this means our empirical formula would now be C1H2O1. However, remember in chemistry, we don't write these ones. We omit this. We don't write this. So you should have CH2O. And that's the difference between an empirical formula, which is this guy. What did I do? An empirical formula, which is this guy, right? And the molecular formula, which is that guy. I hope you can see. Okay, I don't think you can see that. No, good. So a definition of molecular formula, it's the simplest whole number ratio The substance can either be a compound or a molecule. That is the definition of an empirical formula. Right. So obviously in an exam or a test, you won't be given this and then be asked to find that. That is so easy to do. So let me show you how typical molecular or empirical formula questions come. So I think I have, let me see if I can find, I think I had an exam that I saw. Let me see. Mitch. Should have found this one. Okay. I hope you guys can see this. What is it doing? Okay, let's do this. Okay, it's fine. I'll just put it there. Aha, good. So in this example that I saw on the one of the exam papers, I can't remember which year it was. I just took this part because it's gonna be important to explain the empirical and the molecular formula. Right. So our main focus here is 7.7, but based on what we've done in this lesson, we can actually do all of them. We can do this one, we can even do this one. Okay, in that, for this one, you would need the whole reaction. I cropped it off. Okay, let's skip this one for now, because I'd have to find the chemical equation for this. But let's do this one. This is our main focus for now. Right. So what happens is, can I find, yeah. Let me zoom in. Oh, this should be visible enough. I hope. I can't really see. Yeah, I think this should be visible enough. So what I'm saying is, at this point in this lesson, we would be able to do all of them, including this one. I like this one actually. This is the previous one where we were describing volumes and so on. Right. But we can always do it at the end because there's some important concept called limiting reagents that's part of this. Yeah, actually. So now let's focus on 7.7. So in this problem, you are given that a reaction, the reaction above in the first step in the manufacturing of an acid, like I said, I cropped this from a past paper. So unfortunately, there's no chemical equation, but this should be enough. This acid contains 1.59% hydrogen, 22.2% nitrogen, and 76.2% oxygen. So determine the empirical formula of this acid. Now, the first thing you do, you list them. You are told that you have hydrogen, you have nitrogen, and you have oxygen. Now, after listing these things, you give the percentage that they gave you. It must be organized. 22. You write what you know, right? Always. This will look a bit stupid sometimes when you do it because why are you copying the question? But in essence, you're not really copying the question. You're just taking the information that they gave you. 4.2%. Now, what you do, you translate this into masses. Turn them to masses, all of them. So this means you'll have 1.59 grams. Remember, in chemistry, we use grams. You don't divide, or there's no special formula for taking this percentage into grams. Where it all comes from is if you are given a percentage composition, the reason we just take it as is and make it into grams is it was based off of the assumption that the whole compound, or the acid in this case, contains 100 grams. So 1.59% of 100 grams will just give you 1.59 grams. So they based it on that assumption. So whenever you're given percentages, don't even ask. Just start translating it into masses. So this means we will have, actually, let me change color. and use blue. There's no difference though. Let's use this one. 1.5, sorry, 1.59 grams. Okay, after 1.59 grams, we have 22.2 grams. And then this means we have 76.2 grams. Now, there's a table that actually you can make to make your life simple. There's this table that I like doing. It makes life very simple. So now that you have these masses, let's make our table. Once you are used to practicing, you won't even have to list them here. You'll just use the table and list them there. Right? This table is very nice and easy to remember. Your teachers probably would teach you this as well. Some people prefer calculating everything step by step. I say go for the table. It's one of the simplest things you do. Okay, you have that. Right, guys, please give me a second. Just need to close my windows here. There's too much background noise. Okay, that should be better. Now, once you have this, you can start listing your things again. You have C, H, and O. Was it O or am I just? Oh, yes. Not H, N actually. C and O. This is our acid. Now, you have your mass here. You will put your masses there. Here you want your number of moles, which is N is equals to M over M. Okay, this space might not be enough for that. We can just make it a bit longer. Yes, and then here on the last column, you have your ratio. This used to be very helpful back when I was doing grade 11 as well. Now, you take your masses, you have 1.59, you have 22.2, you have 76.2, right? Now you find the number of moles. You know that carbon has a molar mass of 12. So you'll have 1.59 over 12, right? You find it there. Here you'll have 22.2. What's the molar mass of nitrogen? Let me just look it up. Should be around 14. Molar mass. Yes, 14. We have over 14. And the molar mass of oxygen is just 16. Then you can write that there. So 1.59 divided by 12. Let's do that. Should give us 0.13. We stick to 2 decimal places. Always. Excuse me, 22.2 divided by 14 would give us 1.59.
Hello.
Sorry, hello?
Hello. It's supposed to be hydrogen, not carbon.
Yes, thank you very much. Hydrogen.
So-
Yes, thank you. Hydrogen and not carbon. Now, that means here we need to change this to 1, and this will just be 1.59. Thank you for pointing that out. 16. Now we have 4.76. So these are all in moles. This is all in grams. Now what happens is, okay, let's do 22 divided by 14, just to double check that. Yes, 1.59. Now, at this point, you have all your moles. What you do in the ratio, this section, this one, you want to find the ratio of all of these. So you take the smallest number always and divide everything, every answer that you got here. So what's the smallest number? It's 1.59. So you divide this one by 1.59. This will obviously give you a 1. 1.59 divided by 1.59 again. Okay, this is bad. Let me fix that. Let me actually remove this. 1.59 would give you a 1 still. Now 4.76, sorry, divided by 1.59 will give you a 4.76. It will give you 3. Why is it a 3? Because for the ratio, we don't take decimals. We only take whole numbers. So the answer I got here actually was 2.99. And this should be rounded off to a 3. You don't take decimals for the ratio. Never do that. So at this point, we have the ratio of H is to N is to O. What you then do, you take all these numbers. First, you write your H, you write your N, and you write your O. For H, we have 1. For N, we also have 1. However, for O, we have 3. Now, this, ladies and gentlemen, is our empirical formula. This is how you would solve for empirical formula as asked in that question. If you do it like this, even if you don't start here, if you just start listing them in this table, this is a full 5 marks. Right. At this point, we know how to find the empirical formula. Now imagine from this question they say, how will you find the molecular formula? So how you would do that is, this question would have to add you and give you extra details. Say, for instance, they give you that, let me see, H1 14 plus 1 plus 48. Let's see. Sorry, please mute yourself. Right. What they would say is the molecular mass of this unknown acid is, let's say, 126 grams per. Okay. Let me use black. Something like this. They would have to give you this additional piece of information. What this means is, yes, we don't know the actual ratio or the simple whole number ratio of this acid, but we know it has a molecular mass of 126 grams per mole. So now what you do is, we just found that our empirical formula is HNO3, right? You would want to find the molecular mass of the empirical formula. This should be 1 plus 14 plus 3 times 16. This should be 1 plus 14 plus 48. This is approximately 63 grams per mole. Now, what you then do, you find the ratio of MHNO3 the ratio of M Okay, let me write it in words because it might be tricky using symbols. Then you'd have to find the ratio of the empirical to the ratio of empirical formula, molar mass. Keep making silly mistakes. What does that mean? Let me explain. This is the empirical formula as molar mass, right? However, in the problem, we would be given the molecular mass of the molecular formula, not the molecular molar mass. These terms can get a bit weird. Let's do this. Should be read molar. Right. So what essentially they are saying here is, remember our first example? This was the molecular formula. What they are saying is we don't know this molecular formula, but we know it has a molar mass of 126 grams per mole. And then what just happened now is we were able to find this molar mass of the empirical formula. And now we want to go back and find what was the actual molecular formula. So this is what we're trying to do here. So the way you do that is you take the ratio, which is this molar mass of the molecular formula, to the empirical formula, which is this guy. So how do we do that? We say ratio, let's call this ratio R is 126 over 63 grams per mole. If you want, you can put that there, grams per mole. Right. This would give you, should give you 2. So this is the ratio of the molar mass of the empirical formula to the molar mass of the molecular formula. So you take this factor and you multiply, you take this 2 and you say H, let me write it like this, H is too big, H 1 N 1 O, I think this was 3. You multiply everything here by this factor, and this will give you your your molecular formula, which is H2N2O6. This would be your molecular formula. And this example, right? I had to extend the problem, but if you're required to find the molecular formula, they would present it to you in that manner. You have to get an additional piece of information, which is the molar mass of the molecular formula. So now at this point, we have covered we might have to finish this off on another lesson, but we have covered even this part. Now, let's see if we can get to this one in the next, we should do it for the next 10 minutes. Unfortunately, we shouldn't exceed 1.5 hour, you guys should also rest. But if time allows, or if you allow, we can even finish it up until these ones. Now, stoichiometric calculations including limiting reagents. What does that mean? We have covered that. Okay. What is a limiting reagent? Right. A limiting reagent is basically in a reaction, you will have the reactants, right? So as they react with each other, they form the overall product. Right. So one of these reactants will finish faster and will therefore limit the amount of product we can form. Here's a good example. Let's say you want to make muffins, right? If you want to make muffins and you have 20 liters of water or milk, I don't know what you would add in your muffins. However, you have about just 2 kilograms of flour. In that case, we both know, let's say, we both know that the flour will finish before the water. Why? Because there's more water than we can use to make the muffins. You can never, in any world, you can never take 2 kilograms of flour and 10 liters of water or 20 liters of water to make muffins. It just would never work, right? However, you can maybe say 2 kilograms of flour and let's say 2 liters of water. Maybe that would work, but not the whole 20 liters. So this limits the number of muffins that we can make, right? Just know that if you're getting chased by a dog, you and your friend, and the dog catches you first, you were the limiting reagent. Why are you getting caught first? Okay, now, how would it look like in a chemical reaction? Right. So let's see. Let's say you have, say nitrogen maybe react with hydrogen to give ammonia, right? Just a quick example. Say nitrogen. This one is a very, I think we would have to cover it again on our next lesson because I don't think the amount of time we have would do justice to this topic or this part of the topic. But anyways, let's try and do it. So we have, say, nitrogen reacting with hydrogen. Obviously, you would need 3 of these. And then that'll give you that. Is it, let me see, 2. Okay, it looks balanced, yeah. So let's say you have nitrogen reacting with hydrogen to give you ammonia. So this equation, obviously, you would say a mole of nitrogen reacts with about 3 moles of hydrogen to give you 2 moles of ammonia. Right. Okay, let's do. Let me move it like this. So yes, remember what I said, a limiting reagent is the one that will get finished faster, while the opposite of that is what you call an excess reagent. I should be writing these notes for you. I don't know why I'm speaking only. Let's do this. Limiting reagent finishes first. I don't like finishes. It sounds like we're running a race. Gets depleted. Yes, guys, we are doing physics. You should be familiar with such words. Gets depleted first in a reaction. In the case of the dog, though, you would definitely get finished first if you get caught. Now, let's say you have the excess one is just the opposite. Reagent. The excess reagent finishes last or depletes is the remaining one, doesn't finish last actually, remains. Or is not used up. Reaction. Yes, that's how it would work. Okay, let me zoom in a bit. Now let's get an example up here so that you are, let's see if I can get, it's good to have examples for limiting reagents and the other question we just did. It's the easiest way to explain it. I think I had a nice example here. Oh yes, this one. I like this one. No, actually, let's do it on the other page. Quick example. I find most of these examples on past papers. I just never remember which one they are. But I think this one was 2018. Quick example. Okay. Image. Done. Aha. See this right here. So now, check this reaction. They say zinc reacts with sulfuric acid according to the reaction below. Doesn't matter how scary the equation looks, just focus on the fundamentals. Now, the mass of zinc is recorded during the experiment and is shown on the graph below, right? The reaction stops after 2 minutes. Let's check this graph before we even move to the question. This question, by the way, is about limiting reagent and excess reagent, whatever they might ask later. But let's check this graph. So in this graph, they're saying initially we had a mass of zinc being 5 grams. That's our initial mass. How do you know this is your initial mass? Because you know the graph starts at 0. So that means before we started recording, when we were just starting, we had 5 grams of zinc, right? And now as time proceeds, obviously zinc is reacting with this sulfuric acid. And at some point, the reaction stops. So when the reaction stops, zinc has 2 grams. So this is not the right way to write mass. It should be 5 grams, just a normal 5 grams. At 2 minutes, 2 grams of zinc remaining mass. Aha. Remember what I said about stuff that remains and are not completely used in a reaction? Come back here, where is it? Excess reagent remains or is not used up completely in a chemical reaction. Come back here. Zinc is the has remaining mass. Why is zinc's mass not used up completely? Because zinc is an excess. Excess means more than you need. Well, in actual English terms, in physics, it almost means the same thing. Excess reagent in this case. So this means, since there are two reactants here, the zinc reacting with sulfuric acid, it means sulfuric acid is actually our limiting reagent, right? we are sure that we were reacting zinc and sulfuric acid. Zinc remains after the reaction is complete. And zinc, for the fact that it remains, it is definitely an excess reagent. And if zinc is the excess reagent, it means the remaining reactant, which is H2SO4 in our case, that reactant is therefore our limiting reagent. So we can answer this and say H2SO4 or sulfuric acid. It's up to you whether you write it in words or you write it like this. They accept either answer. Now, okay, we have that. Let's do, yes, good. Now, let's do 6.2.2 before we end the session. So this question is saying, what was the initial concentration of the sulfuric acid if 50 cubic centimeters of the acid was used? There's only one acid here. In the reactants, it's sulfuric acid. So it means we were dissolving this zinc in 50 cubic centimeters of sulfuric acid, right? Given. We have volume of H2SO4 being 50 cm3. Remember what we said about converting? We can never use it in this form. So let's convert it. Unless if you're taking ratios of volumes, you can maybe use it in, you can actually use it in that form because the unit will cancel. But in this case, we want concentration. Always convert when you want concentration. Even if you don't know the answer, guys, you get free marks for converting. So that is 50 divided by 1,000 should be 0.05, I think, yeah. Yes. Okay, why is it not fitting? Good. Now, we have that, right? Now, once we have this, we can go back to our problem. What else are we given? We know that initially, right? Initially, we had 5 grams of zinc. Let us find the number of moles of this zinc. So N Zn would be M over M. Okay, we have that. Our mass is 5 grams. Our molar mass should be, is it 35? Let me check the molar mass. See this? Molar mass of zinc. My periodic table is, give me a second, guys, checking my periodic table. Okay.
It's 65.
65, thank you. It's a bit of a hassle having to find it on my gallery, but I have to print it out next time. All right, so 65, 5 divided by 65. Okay. Let's do that. That is 0.08 moles. Good. Zero 0.08 moles. Now we want to know how much zinc reacted with H2SO4. So this is where we would use our ratios. Luckily, our ratio is 1:1. That means 0.08 moles of zinc. Okay, if you put X here, still the same. That means the number of moles of H2SO4 is actually 0.08. Okay, let me just move it to another page, it's fine. Number of moles of H2SO4 is 0.08 mole. Never forget your units. If you do, remember, you're going to kill people one day. You don't need that. Now, at this point in time, we have the number of moles of H2SO4. Now we can find our concentration. Therefore, this is equal to N over V. Okay. Just use black. Ooh, we made a grave mistake here. Sorry, guys. This is supposed to be 3. So remember, 5 is not the whole mass of zinc that reacted. It's actually 3. Apologies for that. I saw it now, because this number is not making sense. So the way we can be sure that the number of moles when we do the ratios for zinc to sulfuric acid is actually the right one is we must make sure that we use the number of moles of the limiting reagent that actually reacted, because 5 grams is not the whole mass of zinc that reacted. Only 3 grams reacted. Why? Because the initial one was 5 and we subtract 2 and it's supposed to be 3 grams. Yes, apologies for all that backtrack. So now we have 3 divided by 65. That is actually the number of moles that reacted. So then we'll use that number of moles that reacted to calculate how much H2SO4 that was used, because the question was asking how much H2SO4 was used. So now let's do that. If they had given, however, the initial volume of H2SO4, the approach that we almost took just right now would be the right approach. But now they gave us the volume of H2SO4 that was used. Right. Don't worry if you're confused. We will clarify it in our following lesson. We will make this example before proceeding. Right. So this means for today, this will be our last example. Now 3 divided by 65 should be 0.04, 0.05. Right. So the 1 is to 0.05 is to 1. We get that it's the same number of moles, right? So the number of moles of H2 that we used are 0.05. We are confident that we used this number of moles for H2SO4. It's because H2SO4 was used up completely and only 3 grams of zinc were used. So knowing the number of moles of zinc that were used and taking the ratio of zinc to sulfuric acid, we would definitely be sure that that's the number of moles that were used for sulfuric acid as well. If here were 2, maybe the number of moles that were used of sulfuric acid would be different, but now it's 1. Right, so let's proceed. So only at this point now, can we find our concentration? C is equals to N over V. So 0.05 over was our volume? 0.05. This is actually 1 mole per cubic decimeter. Luckily for us, it's just 1 mole. Could have been any number. Now, this is the concentration of the sulfuric acid, the initial concentration of the sulfuric acid. All right, guys. So at this point, let's go back. We have covered all the way up until this point. So for the sake of time, we won't be able to do the last 2 points for today, but on our next lesson, we will start on this second last point up until the last point, and then we'll cover the work for that week as well. So with that being said, thank you very much for taking your time to attend, and thank you also, guys, for your ability to stay proactive and actually participate in the lesson. Like, for instance, when one of you told me that I was making a mistake, that's very good. I want you guys to engage and actually pay attention. And remember, always ask questions on the group. We will be gladly ready to assist you with any questions that you have. Yeah, thank you very much and have a great rest of your evening. Oh, I see hands there. Thank you for the hands. See, you guys are clapping. I don't know why are you clapping, but thank you very much. Let's meet again on our next lesson. Ne? For now, let's just pause it here to allow you guys to go do your homework, take a shower, and I don't know, everything else in the world. All right. Bye.
Thank you.